thanks a lot for the invite. So I think I met Voxel51 about 2 years ago on the CVPR in Vancouver, and I mean, I think you guys are pretty cool, and so you just asked me to give a talk. So yeah, it's a nice opportunity, and so just as a quick background, so I work for Continental. I have a team. We work on level 4 autonomous driving, and we especially looking into rare events. So anything out on the road, it can be like a burst tire, or it can be something, even some vulnerable road user or a pallet or whatnot. It can come in a way, and we have to detect it. So yeah, so I'm going to jump right into the topic. So yeah, and we do this multi-modal. So here you can see on the upper part, you can see our truck, and we equip it with cameras, radars, and lidars. So here you also see we laid out some of the objects that we detect, and this is basically our test collection. And I'm going to walk you a bit through what we are doing. So yeah, quick structure of the talk. So I will recap some of the SAE levels and discuss the roads events and rare events. I am giving a concept and a perception stack. And also I'm going to show you a demo on the implementation that we have done so far. And at the end, I will conclude with a verification example. So yeah, so where are we? So we are coming basically from level 2. You can see on the, oh wait, that's the next slide. Sorry about that. So yeah, we're coming from level 2. So basically assisting the driver. So the driver is still in control, and we have to take care about false positives. So now we are going, well, in level 2, basically now it's going more towards hands-free, but still the systems are lean, let's say. So this we try to tackle this with few sensors so that we can roll it out onto the volume market. Level 3, it's rather, let's say, it's rather at the moment it's quite constrained, so it works for lower velocities, and also the ODD is constrained. And the thing is that the budget for the sensors increases significantly. So because the responsibility now is basically given towards the vehicle, and so we not really talk about the driver anymore, but it's more the user. And yeah, as right now level 3 is basically coming up, but from our side at Continental, we are looking at level 4. So here we have basically the most extensive set of sensors. So we talk about passenger, right? So so the passenger usually, so if there's a passenger at all, it can also be that there's basically nobody inside the car, but the passenger could take over control. So here we talk of redundant systems. So we have a main path, we have a backup path. There's no really such a lot of regulations as for level 2. So mostly it's kind of self-imposed regulations. So safety case frameworks. And so on level 4, we see the sensor suite. It includes a lidar sensor, so radar, camera, and lidar is all in there. And yeah, the whole suite of sensor and redundant systems is used. And still, level 4 is limited by an ODD, right? So we will not drive in thunderstorm, but it's kind of defined where we drive, and usually it's starting like in the southern part of the let's say if we're talking about US, we will start in the southern part where the environment conditions are more benign, and then eventually get up more to the north. So yeah, what applications do we see for level 4? So obviously autonomous flight. This is already starting. So Aurora already has trucks out on the road, and so starting in Texas, and as said, the ODD. So basically the operational design domain and the number of roads, it's growing now. The second domain is the robotaxis. So here we see it's still limited to metropoles, and it's yeah, so it's also growing. And for automated valet parking, that's the third domain we see here. It's a growth field, which means that in the future we expect here much more rollout through the vehicles. So now let's come to the rare events that we see on the road. Yeah, so we have, for example, close encounters. We have objects that deviate from a bounding box representation. We have concave surfaces, small objects, objects or events that are rare and hard to train, or objects that are very near and unpredictable, or just night scenarios that limit the sensor range and bring additional complexity to the recognition task. And so now speaking of rare events, so far this has not been covered so much, let's say for level 2, because there was the ISO 26262, so functional safety, and so the functional safety takes care of regular scenarios, as anyway the driver can take care of the rare events. But now on level 3 or level 4, we have to take care on the system level for this. And so we see the ISO 21448, which kind of tries to encounter or to limit the to give the limits for the performance and to see to basically give the limits for the ODD. And so just I put here 3 examples from the ISO 21448. So safety of the intended functionality. So one example is a boundary, lane boundary on the highway, and you can imagine there's some road debris which is falsely detected as a lane, right? This could be happening in maybe 1% or less than 1% of the cases, but still it's something that needs to be taken care. Or you could have some drawing on the road or some drawing on a vehicle in front of you, which resembles some real life objects. It's only 2D, but your sensor system kind of translates it to 3D. Also depends on which sensors you have available on your system, and so this can also lead to a potential malfunction that you need to take care of from the system architecture. So there's a lot of events of that. So these events also are kind of try to be classified. So anomalies, out of distribution. Then we have like edge cases, which have basically one not normal situation, or also corner cases, which have like a combination of irregular situations or behaviors. So and and also, of course, there is some misuse, right? That we could think of, or yeah, you know, basically someone trying to manipulate the system, or someone trying to manipulate the environment, and in the end, the vehicle is in control, right? So there's this all has to be taken care, and yeah, you will already see that you need that you need much more effort for this than just taking care of the regular scenarios. So yeah, let's take a look how to tackle this. So one goal is basically to maximize operation and also to maximize miles. So we need to enable to early have a decision on having a change in the strategy to reduce velocity, or to circumvent some obstacle, or even to override it or to overrun it, depending on the height, right? So let's say you have a very small object, 5 centimeters. Probably you don't want to drive with the tires above it, because it could be kind of uncomfortable even for the load. But you could try to override it, right? So the clearance of your truck is above these 5 centimeters. So if you're pretty sure what kind of object is in front of you, you could go into this override scenario. Yeah. So, but we need to detect road debris, any lost cargo, vulnerable road users, or any of these combinations. So then we need to define the requirements for the systems and the sensors. That's where we started. And of course, we need multiple sensors. So as there is a multitude of situations, and these sensors usually have orthogonal capabilities, right? So with the camera, you have a really high resolution, so you can really see very far ahead. With the stereo camera, you can also have a disparity map, so you could easily look up to 400 meters and detect an object with a high resolution stereo camera. But you will be limited by lighting conditions, right? And even some weather phenomena in front of you. If you have a radar, however, bad weather, it's not such a has not such an influence, but the resolution is much lower. With the Lidar, you have a really high resolution. You can also kind of see through any glass objects. You have really less. You're not at all bothered by lighting conditions. So all of these sensors basically you want to have on board when you want to have a safe decision on what is in front of you. And but as the situations are not really, you cannot let's say drive like 1 billion miles or 10 billion miles to get any event. So you want to have some synthetic data. You want to have a test catalog and vary it, and so that you cover all of the foreseeable rare scenarios. And of course, some synthetic data and hybrid data. I think this is nowadays still a challenge to create very authentic, realistic hybrid data. But that's also what we are using, and here we also see a big option. I mean, there is also scenarios where you, let's say, one car drives 100 kph, so something like 70 miles per hour. The oncoming car also drives this fast. It's even dangerous to drive this use case. So you would rather avoid that and do this with synthetic data. So yeah, and then of course you need KPIs to really be sure that that you reach the goals. And yeah, data mining is very important. so to find anything that you recorded out in the field operational test. So yeah, so perception approaches. So how to do this rare event stack. So one option is to do it geometrically unsupervised. So basically, it's kind of maybe what you would call software 1.0. So and you really cannot do it with camera only. You need lidar and radar for that. But then you can then you basically can craft your decision trees. Supervise, of course, you will also come to high result to high performance. You might suffer from out of distribution problems. Deep learning or end-to-end. Now it's basically coming up to just drive end-to-end, to just have the perception end-to-end. So yeah, you can see on the right side a bird's eye view. That's one very popular approach nowadays. You have some hats on this for traffic participants, for lane, for voxel. So I guess this could all be seen on previous CVPRs already. One thing to mention here, so closed set detectors versus open set detectors. So for rare events, we see that if we have a closed set detector, we will not really be able to tackle it, as we cannot really have everything in the training set. So yeah, these are things to consider and to when basically designing your perception stack. And so just a quick recap. So what we want to detect is any non-infrastructure object. So we want to avoid any out of distribution problems, right? So we think we need active sensors for that. We cannot do it with camera only. All of these sensors need to be synced, of course, especially for any events up front. We use the front bundle of the sensors. We also have some system limitations, right, which are derived from the sensors, so mainly the resolution. So any active sensors, the main task, well, the main challenge now is to come down to the needed resolution. So you can think of, let's say, detecting a lost cargo object, let's say 0.2 by 0.2 or 0.3 meters. To detect it in, let's say, 180 meters, you need a really high resolution, so much less than 0.1 degree vertically and horizontally. So yeah, so based on the sensors, we get these system limitations. We need this extensive test catalog, and so and we target high detection rates, so we will not miss out anything, right? So we don't want to have any false negative in our perception results. And so yeah, it really depends on where we run, on the CPU or on the GPU processing island. So basically choosing the different stack approaches that you just showed saw one slide earlier. Yeah, so let's go into our implementation, and I just have a video here I would like to show to you. So yeah, we are here on a proving ground, so in Germany, and so you can see we are driving on this highway, let's say. And on the right side, we place our objects, and so yeah, you can see here basically good weather conditions, right? It's a bit overcast, but it's really clear sight, and so we are in the truck. The sensors are all running, so you can see on the right side is the lidar point cloud. On the left is the camera. So we basically project the LiDAR detections into the camera. And yeah, right now we are basically detecting these objects, logging them, and running our KPIs on that. We also place some objects, let's say some reference objects here, so stop signs that we can in the raw data easily detect, like where we're at in the in this scenario. Also, we have some pedestrians walking, so just to have some more yeah, have basically more information in the data. And so yeah, of course, we also store all of the ground truths here. So we yeah, so we can basically run automated KPIs. And typically we do like different approaches, different velocities, ideally different weather conditions, and also at day and night, and have some statistically significant repetition of the data. So yeah, okay, let's go to the next one. So here we are in Frankfurt. So it's basically on also on a proving ground. It's kind of a private proving ground just behind the Conti facilities. And yeah, on this day it was pretty nice. So we had a different variation of weather, and so especially even if you don't have directly rain, but you have kind of a wet road, it has a direct influence on your sensor readings. So let's say for the LiDAR, the wet road acts like similar like a mirror, right? So your rays of light are reflected from the road, and so yeah, you of course you deal with multi-channel with multi-channel returns, and so yeah, it's just more difficult here in this rain situation. So yeah, so basically we need a lot of data as well. So so here we just recorded LiDAR and camera. So we built up our internal data sets. Also, we use public data sets. So for example, there's lost and found. There is a data set, but meanwhile, there's more data sets also published on lost cargo or also on rare events. I think it's still a kind of a relatively new field to yeah, so we but definitely multitude of variation is here really appreciated. And so yeah, so even let's say you have some dummies or some, well, there's no really pedestrians who would lie on the road, but usually we work with dummies. I think here you see this child, but it's yeah, we also vary it, let's say, with different clothes. So even if the color of the clothes change, the perception could be different, or the sensing could be different of the same object, but just having different textile on. And so also the road surface, it's already, as mentioned, it's very important. As you can imagine that you so we don't want to detect road, but the objects on the road. And so typically the road has also a standard deviation, right? So even with reading the road with a LiDAR sensor, we don't get like a flat plane, but you have a standard deviation. And so you have probably like ±7 centimeters standard deviation on the road. And then it's pretty hard to detect an object of 5 centimeters height, right? Because it's just in your standard deviation of the road. So, but it really depends on the quality of the sensors and of the data with that. So, as mentioned, we have some we also create our artificial data. So here on the right side, you can see we have basically it's a wooden bar, and we simulated the pitch on that, so that we can run some use cases on it, and it's really helpful, not only for any debugging, but also for running KPIs and having some some corner or edge or corner cases. So so here we have a result, let's say for a tire. So like how so we so here you see basically on the upper left, you see when we first detect the tire, and then relevant for us is the height, also the width, also the lateral position, so that we can make a driving decision if we override it, let's say, or if we overrun it with the tires, or if we need to stop, or even if we need to evade it. So let's say we change the lane, and so yeah, we are still in development for this. Yeah, I'm just showing you here some results from in between. Yeah, so let me come to the conclusion. So we are a system provider for SAE level 2 to 4. So Continental, we produce components. So let's say the ADCU, so the central processing unit, also the sensors. We use the Lidar in our L4 system. So we don't think we can go without Lidar or multiple Lidars. And we developed this rare events detection path, which we prominently use the Lidar to detect objects. And yeah, we're really up to cooperation. So if you think this is interesting for you, if you're from an OEM side, or if you're just interested in this topic to have discussions, just get in touch with us, and yeah, we're happy to go into more details.
Fantastic. So we do have one question, and I'll go ahead and read it out. I'll actually change it a little bit so it's maybe covers a broader topic area. But the question came in around how are you accounting with your sensors, your cameras, your LiDAR for adverse weather conditions where you might have rain on a camera, you might have debris, dust, maybe even oversaturation of light. How do you deal with these harsh environments in regards to the sensors that you're using to generate data?
Yeah, thanks for that question. This is really, I mean, this can really totally make the difference, right? So I mean, obviously, as said, at the moment we kind of start in benign conditions. So and you can define in your ODD, so in your operational design domain, you can pretty much define your weather conditions. So you can say up to so and so millimeters of rain per square meter, you still want to drive, right? When it's above, then you would kind of tailor operate it or go into the hub or whatever. But of course, going on, we want to tackle more miles, more roads, and then also more severe weather, obviously. So we really want to replace the driver, or let's say first we want to kind of bridge the gap of missing 80,000 drivers missing in US. That's the number I heard. And so so what we need here is let's say heating of the sensor when, so let's say in cold conditions. So the LiDAR, for example, it needs to be stable on a certain temperature, so we need to heat it. Potentially, we would also need to cool it, so basically some temperature control of the sensors. And then when you get different dusts or any blockage or so, you first want to detect it, of course, within an appropriate time. and you want to take countermeasures. So so similar, we have some wipe. So well, we have basically, I think we have air basically, so to blow it off, to blow any dust off, or also like some liquids, like similar to water, but different composition, and so we can also wash the dust away. Can happen multiple times, and so yeah, this would be the solution. And then of course also you wanna calibrate the sensors, right? So you hit something, or a bird hits the sensor and it's slightly miscalibrated, so it's pitching down a bit. Then you really want to know it, right? Because you would derive some wrong assumptions from the sensor now. And so we regularly calibrate the sensor, and when the car is going in the hub, for example, and so this would be kind of a, let's say, maintenance cycle.
Fantastic. So let's take two more quick questions, and I'll kind of executive summary the next one, which is around data sets. I think you did mention that there are public data sets as well as data sets that you curate yourself. The question was, do you collect very specific data sets, or are there public data sets that you can recommend that zero in on some of these adverse weather conditions like rain, snow, dust, etc.? Or do you just go with a broad data set, let's just say news scenes or something like that, and then use embeddings to kind of find, these specific weather conditions, whether they be snow, whether they be rain, driving into a tunnel, or things like that? What kind of information can you give us around finding specific data sets or using existing data sets to hone in on these adverse weather conditions?
Yeah. Yeah, I mean, one thing is it really depends on your classifier, right? So also like how well your classifier needs to be tuned on your data. So you could be kind of limited in using data with, let's say, different mounting positions, or even completely different imager or different scan pattern for the LiDAR. So in the end, you would really need to collect data yourself with your target sensor set. And if you're a tier 1 as Continental, you do this while developing the sensor. So you have like an A sample, B sample, C sample, and you always change the components of your sensors. So you constantly taking new data and updating your algorithms and your classifiers. But of course, I mean, there's really the need for kind of generalizing the data, right? So that's not every time everyone needs to collect new data. So let's say domain adaptation, and we are also trying that, and also like with hybrid data. So we could let's say have like a benign condition and add some artifacts to it, right? Or add certain objects to it. So I think we're looking into all of these options. Yeah, but it's what you have to do in the end to reach a really high performance.
Excellent. So we'll take one last question before we move on to Chong Kung's talk. How is radar data fed into the model? Is it pre-processed, point cloud from Doppler and other processing, or raw data? So I guess the question is around what the data processing flow looks like when data enters the sensors.
Yeah, that's a nice question. So as you know, we have quite a history of radar development, and so actually we do both. So we use radar data as a point cloud. So let's say detection. So you have the cross section, you have the XYZ, and the Doppler. But you can also start earlier, right? So you have the data cube, so you have the different FFTs, and we are also trying to directly look into the raw data and learn from the raw data. Yeah, so that's let's say both approaches to which we don't really can tell right now. One is better than the other.